Bien, bonjour à tous. Donc aujourd'hui, on a un séminaire exceptionnel à l'Institut. On a la chance de recevoir Pedro Ponte Castañeda, qui est professeur de mécanique à l'Université de Pennsylvanie. Donc Pedro a de nombreuses connexions avec la France depuis longtemps. Il a été, donc, je pourrais facilement dire, vous le connaissez tous, mais je vais quand même dire quelques mots. Il a été donc invité chercheur CNRS dans les années 90 à Marseille. Ça a été le début d'une longue collaboration, notamment avec l'équipe de Pierre Suquet. Et il a été également professeur à l'école polytechnique au cours des années 2000. Et à cette époque-là, donc, tu as formé beaucoup d'étudiants qui ont poursuivi leur carrière dans la communauté ici, et notamment au CNRS. Je pense en particulier à Costas Danas, par exemple, qu'on connaît, ou François Villot, Oscar Lopez, qui est aux États-Unis. Donc Pedro, pourquoi est-ce qu'on le connaît tous? Parce qu'en fait, il est à l'origine d'un renouveau des méthodes d'homogénéisation pour les comportements non linéaires avec des approches variationnelles. Et ces approches donc, qui datent donc, du début des années 90 ont ouvert un champ de recherche très fécond qui est toujours très actif. Et elles se sont diffusées au sein de nombreuses communautés en mécanique des matériaux grâce aux liens forts que tu as tissés. Donc je cite quelques exemples de contributions, notamment sur la rupture ductile, sur le comportement plastique des matériaux polycristallins, sur les matériaux fonctionnels comme les élastomères diélectriques. Je vais pas tout citer, aussi t'intéresser beaucoup aux instabilités. Oui, voilà, c'est ça. Aux instabilités dans les élastomères. Et donc je voulais citer aussi, donc il y a un article c'est vrai qui a fait référence, qui est nonlinear composite. Je pense qu'il y a un article de chevet pour beaucoup d'entre nous que tu as coécrit avec Pierre Suquet à la fin des années 90. Et donc Pedro est éditeur associé au JMPS et au journal d'élasticité. Donc voilà, maintenant et les travaux sur les fluides complexes plus récemment. Donc voilà, c'est vraiment un grand plaisir pour nous de t'accueillir aujourd'hui. Et donc je te laisse présenter.
But I can manage to find the on-off button, I think. It works now? Great. So, yeah, so again, it's a great pleasure to be here today. I'll do my, my presentation in English, otherwise not so comfortable, especially at this time in the morning, speaking French. I'm going to tell you about some recent things that we've done in this area of nonlinear homogenization. In particular, something that maybe hasn't been around that long, this fully optimized second order method, and also some recent estimates for particular composites. And then I'll try to give some applications for composites, and then if I have time, for polycrystals. So I think I don't need to to tell you that most materials, right, are heterogeneous at small enough length scales, even before you get to the atomic level. These are just going to flash quickly some examples of metal-based composites, polymer-based things, rubber tires, rubber foams, etc. Geomaterials. I'm visiting at NSAM, working a little bit with Olivier Castelnau. He's interested in these geomaterials like olivine and ice. We had a project, I don't know if I have time to tell you a little bit about this at the end, but on sea ice. Sea ice is a very interesting material that has microstructure at two different scales because being ice is a polycrystal, but in addition, it has these pockets of salty water, brine, and so it's a multi-scale material, and the microstructure gives it some very interesting properties. It's also, of course, very important these days. because of the albedo effect, right? Sea ice covers a large part, or used to cover at least a large part of the Arctic Ocean. And very recently we've gotten interested in particle suspensions. So these are things where you have elastic or viscoelastic materials in a fluid. So homogenization again is concerned with replacing the properties of a heterogeneous medium, right, by something with homogeneous properties. And the idea is that if you have separational length scales, you can do this, and the effective properties that will characterize the macroscopic response of the heterogeneous material will depend on the properties of the faces and the microstructure, but not on the specific boundary conditions, right? And so the idea then is that you can make use of this this fictitious homogeneous material instead of the complicated heterogeneous material, and do your usual calculations at the higher length scales. So in a sense, what we're doing here is continuum mechanics, but for the constitutive models, right, we're trying to develop things or models that bring in the effect of the microstructure. And microstructure, of course, comes in many different forms. The other thing is, right, in sufficiently large fields, you have nonlinear behavior, so you have to take that into account. Materials may respond to different types of fields, and so you can have things that are multi-physics. And if you have large deformations, as some of the examples that I showed, then the microstructure can evolve, and that has to be taken into account. Damage is an example of something that evolves, and you can have also possible development of instabilities. So yeah, you want to develop models that can capture at least some of these features, depending on the model on the material system that you're interested in. But the objective is not to get results that are not just to get results that are accurate. You can do that with numerical simulations. The objective is to do this in a way that is simple enough, right, so that then you can use those models in standard FEM codes, for example, for computations at the higher length scales, at the structural length scales. So I've chosen to speak today about the application of these methods in the context of plasticity and viscoplasticity, typically associated with behavior of metals, but it can also be polymers. And as you'll see, there are also complex fluids that can be described with these kinds of models. The basic equations are well known to all of us, right? So I'm going to write them in terms of nonlinear elasticity or viscoplasticity. This is the strain related to the displacement, or the strain rate, the rate of deformation tensor related to the velocity. And this is the equilibrium equation. Again, depending on whether you're thinking about linearized elasticity, sigma is infinitesimal stress tensor, or if you're doing viscoplasticity, sigma would be the Cauchy stress tensor. In which case, if you're doing viscoplasticity, this would be a snapshot of the microstructure at some time, right, which may be evolving with the deformation. Anyway, the constitutive relation, and this is the main thing that I want to discuss in this talk, is given by the derivative of a stress potential with respect to the stress. And the thing is that this stress potential corresponds to nonlinear constitutive response, meaning there's a nonlinear relation between the strain or strain rate and the stress. And so the potential will be assumed to be convex, which is appropriate for viscoplasticity. But it may be isotropic, in which case is a function just of the equivalent or von Mises stress, or it could be anisotropic. This is a model that is used for crystal plasticity in terms of some slip potentials that are functions of the resolved shear stresses. The behavior of these heterogeneous materials is characterized in terms of these functions chi r that describe the microstructure, and potentials which now have the superscript r that defines the faces, right? So this is the constitutive behavior of this heterogeneous material in terms of the heterogeneity that's contained in these functions chi r. And the effective or macroscopic behavior you can show involves a stress potential that is obtained from a variational principle, right? And the property of this stress potential, as was found by Hill many years ago, is that it has the same structure as the local constitutive relation. So if you differentiate it, this time with respect to the macroscopic stress, you get the macroscopic strain or strain rate. So our objective will be to get estimates for U tilde, right, in terms of the properties of the faces and the microstructure. However, we're going to be looking at most of the systems that I showed you, right? The microstructure is random. We don't know exactly what we have. Maybe what we know something about the microstructure, things like maybe the volume fraction of the faces, right? The porosity, or if you're lucky, some information on 2-point statistics, right? Is the distribution of the materials isotropic, for example? We may know something about the particle shape, if there are particles in the system. So we're going to make use of these microstructural variables, but we will not be able to incorporate all the microstructure in all this gory detail, right? The good thing is that because we're doing averaging, right? You know, some of the details sort of don't matter so much, okay? But we have to keep in mind that when we do these calculations, right, we are aiming to get some description of the macroscopic behavior. And that is what is going to be characterized by this effective potential U tilde. In addition, we'll be able to get, and this is something that's maybe not appreciated as much, is we can also get information on the field statistics, right? As I said, you know, this is a random system, so there are, you know, you have macroscopic average, that's great, but you may want to know something also about how the fields are distributed in this heterogeneous material. And that's, you know, that can be characterized by things like phase averages, right? As well as second moments, or the covariance tensor of the second moments, or covariance tensor of the fluctuations, right? So this is a measure of how the fields are varying in a phase, for example. And there are some identities that you can use, for example, to compute the average. Remember that this is a nonlinear constitutive behavior, right? By basically making use of results of this type, right? But with perturbations, right? You perturb the result through, in this case, something that is linear in the stress, and by solving that problem for that fictitious material with the perturbation, right? You can then get an estimate for the average of the stress in phase R by taking derivatives with respect to the corresponding parameter. So that's what we can do. What we cannot do is, right, using these methods, we cannot tell you the strain field at this point will be such and such, because, right, it's a random microstructure. You don't know exactly what you have at that point. You have probabilities of having one phase or the other. All right, so let me start with this fully optimized second order method, which is concerned with how do we deal with the nonlinearity in the phases. I'm talking about the nonlinearity in the constitutive response. So if this is the stress as a function of the strain, right, the constitutive relation may be something like this blue line here. It's nonlinear. And yeah, so unfortunately, the methods that have been used very effectively to get information on the microscopic response of composite materials or heterogeneous materials with linear constitutive behavior don't work for nonlinear materials, right? Methods based on things like Green's functions and standard results from theory of linear PDEs. So we have to think of some linearization, right? In this case, the material behavior that we're interested in is not weakly nonlinear. It's, plasticity is strongly nonlinear, so we cannot do perturbations about some small parameter. And in addition, when you have a heterogeneous material, even if the faces are homogeneous, the fields will be inhomogeneous or non-uniform in the faces. So you have, if you want to linearize, right, you need to know two things. First thing is, what do you linearize about? And the second thing is, what type of linearization should you use? Right? This is a tangent, and this is a secant linearization. And the idea, which goes back a while, is, well, we're not going to guess what this linearization should be. We're going to design variational principles, right, for a linear comparison composite that will tell us what the optimal linearization will be. At least within the context of something that has to do with the problem that we're dealing with, which is this variational representation of the macroscopic potential. So we introduce this linear comparison composite, which has the same microstructure as your nonlinear. So this is just for one realization of the material, right? But the stress potentials are quadratic in the stress, right? And they depend on some viscous compliance if you're doing viscoplasticity, and some eigen strain rate, or if you like, strain rate polarization. Because when you differentiate this thing with respect to the stress, this is the constitutive relation that you get, right? And this is something that is analogous to a thermoelastic material, right? Because you have linear elastic, and then you have a strain rate, or a strain if you're doing thermoelasticity, that would be prescribed, right? And that would be constant in the faces if you're doing classical sort of thermoelasticity. So this is a homogenization problem that we know how to solve, right? And so it's described in terms of a macroscopic stress potential, and it's known that being the response being linear, the macroscopic potential can be described in terms of these effective coefficients, m tilde, an effective viscosity tensor, gamma tilde, an effective thermal strain, except that we're not doing thermoelasticity here, right? We're just using the fact that this linear comparison composite, right, is analogous to something that we already know how to homogenize. On the other hand, for the field statistics, the formula that I gave you earlier simplify, because the material is quadratic, and well, not quadratic, corresponds to linear behavior, and then you can get the first moments and the second moments using these relations that go back a while, and you therefore can also get information on the covariance tensor of the fluctuations. You introduce this linear comparison material that has the same microstructure as the nonlinear, the same class of microstructures as the nonlinear, because remember, we're doing this for a random system. So, right, the volume fractions will be the same, the pair correlation functions for the distribution of the faces will be the same. The only difference is the material behavior is different. In the problem that we're interested in, the material behavior is nonlinear, but this is what we know, linear. So how do we get to the nonlinear problem? Well, we can write the potential for the nonlinear material in terms of the potential of the linear material, right, that we just described, plus some correction. And the correction is clear what it is, right? This not doing anything. I'm introducing these, I could just do one of these, but I'm doing two with some weight factors, and the reasons will become evident in a minute. But yeah, so there's nothing here. These shifted potentials, right, are also nonlinear. Now, the key result is that we can actually get back to the nonlinear potential by doing this process here, where we look at the stationary points of the difference function here, right? And when you do this, these stationary points of the difference, right, you end up with something that doesn't depend on the stress. It depends on the properties of the linear comparison medium. These things are functions of the linear comparison medium. And this is the potential of the nonlinear, of the linear comparison medium, which depends on the stress and on the properties of the medium, right? These are the properties of the linear comparison medium. And if you take this combination of things and then you compute the stationary points with respect to these variables, you can show that you recover the nonlinear potential. This is some sort of very generalized Legendre-Fenchel transform. You do the Legendre-Fenchel transform twice, you get back to the original function. Yeah.
It's convex here.
Well, no, and that's the reason why we're using stationary points and not minima or maxima, because, well, yeah. Here's an example, right? If you take the stress potential to be power law, right, some power 3, and you take this general quadratic potential for the linear comparison, you look at the difference, this is what the function looks like, right? It's not convex. You have local maxima, local minima, you have saddle points, you have global minimum, you have lots of stationary points, right? So in our first work, going back to a long time ago, we looked for the minimum, right? And when we did that, we had a formula like the one that I just showed that involved just computing the minima. The problem with that is that the results you get are bounds, right? It's good to have a bound, right? You know the sign of the error. But because it's a bound, you're giving away some information, right? And the point here is that if you are prepared to work a bit harder and use not just the global minimum, but the all or more stationary points, you can actually get more accurate results, even if they're not bounds. So that's the basic idea. In any event, at each of these stationary points, you can define an error function, right, that depends on the properties of the linear comparison medium. These functions encode information about the nonlinearity because they encode information about the difference between your linear comparison medium that depends on these properties and the nonlinear medium. Okay, and that's the reason why, right, you can recover the nonlinear potential by doing this procedure with a linearized potential and these things, which are these functions here, right, that encode the information about the nonlinearity of the material. In any case, if you make use of those results for the stress potentials of the faces, you could get a corresponding result for the effective potential of the composite. And it's not an exact result. It's an estimate. It's a variational estimate that looks like this, right? The effective potential of the linear comparison medium, which we know how to generate, right? We know how to do. And this combination of things that depend on the nonlinearity of the faces. So, as I mentioned, this is you have to do these compute these stationary points, and that gives you a result that is an approximation to the nonlinear potential. If as I mentioned, you wanted to make use of the local or global maxima or minima, then you'd have something like this, which would give you a bound. And so, in a sense, this new result here is complementary to these bounds. Now, how do we interpret it physically? One way to interpret it is when we look at the stationary conditions, right? We have stationary conditions of this type here, right? And these conditions give us something that basically correspond to a generalized secant equation. And then you have these stationary conditions here that come from taking derivatives with respect to the strain rates and setting them equal to 0, and derivatives with respect to the viscous compliances and setting them equal to 0. What you can see is you have relations between these stationary points and the first and the second moments of the stress. These equations here can be written in this form, and this looks like, right, some linear approximation to the nonlinear function. In fact, this is a tensorial relation, but if you wanted to do a one-dimensional cartoon of this, right, you have this blue line here, which is nonlinear, right? And you have this linear response, the linear comparison, and it interpolates between these 2 points, right, which I call sigma hat and sigma check. Don't worry about the the superscripts are just the faces. The subscripts are the multiplicity of stationary points, because you can do this at different stationary points. In any case, the first condition, this condition, is just, right, a generalized, I call it a generalized secant approximation. So that's the first thing. And then the other condition, this condition here, right, tells you that, and this is where these weight factors appear, right, that the weighted average of these interpolating points, sigma check and sigma hat, should be related to the average stress in the linear comparison composite, which I told you I can estimate. So that's the first thing. The other condition, this condition is more complicated because it involves the covariance tensor of the fluctuations. That's a fourth order tensor, actually. And so I can't draw a picture of that. But what I can do is do a two-dimensional picture of, right? So this is this is a plot of the various stationary points. This is attempting to describe these points here, right? The points here, there, right? And the condition on the fluctuations, right, is given by this. So the fluctuation tensor, right, has to be related to the differences between the hats and the checks, right? And so this construction here, right, is a little bit complicated, but it's required by the fact that this tensor here is a high rank fourth order tensor. So you need to make use of all the stationary points in these error functions in order to be able to satisfy this condition on the fluctuations. In earlier work, we had tried to satisfy this condition with only a couple of these things, but as you can see, it's impossible because you can't construct a general fourth order rank tensor with just a couple of second order tensors. And this is the reason for, you see, this is a sum from p equals 1 to m, where m is the number of stationary points. So this is a little little too detailed, maybe too much detail, but just to give you an idea of the basic method and how you can try to generate information on a linear, on a nonlinear material using linear properties. And that requires this rather complex linearization process that takes advantage of your information on the first moments and the second moments of the fluctuations in this linearized material. Once you do that, then the rest is is very nice because as a consequence of having something that is fully optimized, you satisfy all the stationarity conditions, the macroscopic constitutive relation for the nonlinear material can be expressed exactly in terms of the properties of the linear comparison medium. Right? So this is the constitutive relation for the linear comparison medium. Right? But the n tilde and the gamma tilde depend on the properties of this linear comparison medium, and I just told you how to compute those things. And of course, it depends on the nonlinearity, depends on the microstructure, and it depends on, right, how this microstructure and nonlinearity, right, leads to a distribution of stress fields in the composite with a given microstructure. But in the end, you just have this relation for the macroscopic strain rate, and it's also nice that you can extract information on the first and the second moments, as well as the covariance tensor of the fluctuations, right, directly from the corresponding quantities for the linear comparison medium. So let me now show an application of this, and I can see that I'm going very slowly, but okay. This is the microstructures that we're interested in. Random distribution of ellipsoidal inclusions. Inclusions don't have to be exactly ellipsoidal, but you know, anything can be approximated with an ellipsoid. Right? It's better than approximating them with a sphere, if you like. And there are these dashed lines, and the dashed lines correspond to the shape of the distribution, the angular distribution, meaning the pair correlation function for the distribution of these particles. And so that gives you two shape tensors that describe those variables, and you can make use of that information through a variational approximation of the Hashing-Strickman type that leads to something that looks like this. I don't have time to go through all the details, but now I'm now working with the dual formulation in terms of the dissipation potential. So W tilde is a function of the rate of deformation tensor. D bar, I called it epsilon in the previous slides. Now it's rate of deformation tensor D bar, and it has this term that is quadratic on some reference medium, uniform reference medium, L naught, the microscopic strain rate, of course, and then these equations that describe the polarization fields in the faces of this linear composite. The key thing is this microstructural tensor here, ERS, that depends on two SLB tensors, PR and PD. PR describes the shape of each family of inclusions, right? And PD describes the shape of the distributions of these inclusions. And I'm assuming for simplicity that the distribution of all the inclusions is the same, okay? But you don't have to do that. The distribution of inclusions could be different, but there is a requirement that comes from the definition of these pair correlation functions that the distribution of one family of inclusions relative to the other family has to be reciprocal, meaning that the other family, the distribution of this family with the other family has to have the same shape. So that puts some restrictions, and of course those restrictions are automatically satisfied by assuming that that the shape is the same for all the distribution is the same for all the inclusions. In any event, those variational approximations of the Hashing-Strickman type make use of a reference medium, L naught, which is arbitrary. In the first application of these ideas, L naught was chosen either equal to it was shown that if it's chosen equal to the most compliant medium or the stiffest medium, right, you get upper and lower bounds. And this is consistent with the idea that you have a medium that is random, right? So you don't know exactly what the properties are. If all you know is the faces and pair correlation function of how they're distributed, that means that in principle you have a range of possible behaviors, and the Hashing-Strickman bounds characterize that. The way we're using the result here, we are assuming something about the microstructure. We're assuming that we have inclusions of one material, let's say, in another phase, right? So that already says a lot about the microstructure. And so the results are not necessarily bounds anymore, but we have the same issue in that this reference medium is arbitrary. You can choose it to be anything you like, right? The question is, how do we choose it? Well, for a distribution of particles in a homogeneous medium, we know that in the dilute limit, right, when you have dilute concentration of particles, we know the exact result. This goes back to Eshelby, right? So in that context, it's natural to choose the properties of this reference medium to recover that result. And the way you can do that is by choosing this property of the reference medium equal to property of the matrix, right? And so that is a natural choice for this reference medium. And in fact, that's what we did in this work with Willis. And we generated some estimates that recovered the dilute limit exactly and gave you results that actually, in some cases, were bounds for these particular microstructures. But being bounds, it meant that for most microstructures, they were either too soft or too stiff. And so in an attempt to try to generate more accurate estimates for particular microstructures, we realized that we could make other choices for L0, right? And this is a bit of empiricism here, but it's empiricism that is consistent with the with this, if you like, statistical approach to the properties of these composites. So if you choose the L0, this reference medium in the homogeneous reference medium for the Hashing-Strickman estimates, and you set it equal to L tilde, the effective viscosity tensor of the composite, which you don't know, you generate an equation that, an implicit equation for this L tilde, right? And you can solve that equation, and it turns out to be the same equation as the self-consistent method, right? Yeah, so that is that provides, if you like, a more rigorous derivation of the self-consistent estimate. It's not an inclusion in an effective medium, but it's, you know, it corresponds to a distribution of particles with a given shape and a given pair correlation function in this matrix material, right? This effective medium approximation has some interesting properties. It also linearizes for dilute concentrations, is also a good estimate, but once you get to large volume fractions, particularly if particles are rigid, you get a percolation phenomenon where the properties blow up at a finite concentration of particles, and that, for spherical particles, that value is too low. It's something like 40%. So most materials, most particulate systems don't do that. The answer is somewhere in between the PCW estimates and the self-consistent estimates. So it's natural to think of some sort of interpolation between them, right? And we proposed this use of a self-consistent prescription interpolating between L1 and L tilde. This is the self-consistent equation for a two-phase medium with properties L1 and L tilde. But now there's a parameter lambda. It's not a volume fraction anymore. This is the interpolating parameter that it's trying to give you information on this additional microstructural variable that we cannot extract directly from these Hashing-Strickman type variational principles. But the property is that if L0 is equal to 0, then L if lambda naught is equal to 0, then L naught is equal to 1, and if lambda naught is equal to 1, then L naught is equal to L tilde. So that means that this procedure recovers the PCW estimates in one limit and the self-consistent in the other. And so hopefully for intermediate values of this parameter, we can try to get improved estimates. So you can do this for two-phase materials, and this is the set of equations that you get, right? So this is a set of equations that allows you to compute L tilde given L1, L2, the volume fractions, and this microstructural information about the shape of the inclusions and how they're distributed in space. So what happens if you try the simplest case, an isotropic distribution of spherical rigid particles? You get a result that looks like this. The effective viscosity divided by the viscosity of the suspending material, viscosity, so it's a fluid, a Newtonian fluid if you like, is given by this formula here that involves phi. Sorry about the change in notation. Phi is the volume fraction, and lambda is this interpolating parameter. So when lambda is equal to 1, this is the Hashing-Strickman lower bound. When lambda is equal to, when lambda is equal to 0 is the Hashing-Strickman bound. When lambda is equal to 1, this gives you the self-consistent estimate for this particular type of microstructures. In between, you get something that is in between the two results, and that means that now we have a rigidity threshold, right? So this thing blows up when phi m reaches this value that depends on lambda. So you see when lambda is equal to 1, this gives you 40%, which is a self-consistent estimate. So this is the simplest case that you can do, but you know, all this work is not worth for doing, is not necessary for getting something like this. You can generate something like this from some empirical relation directly, but when we apply this to the nonlinear materials, we want to be able to do this for something with anisotropic faces, for example. So this thing is no longer a scalar, it's a tensor. So then how, you know, if you wanted to do that, determine an empirical relation for a tensor, that becomes much more complicated. And if you have shapes, then it becomes even more complicated. So the power of the Hashing-Strickman type variational principles helps you to reduce everything to just one parameter that as we'll see, attempts to account for the interactions between the particles. So anyway, it turns out that for this systems, it's just a lot easier to do the experiments for a fluid. There's an analogy, right, between elasticity for small strains and viscosity of suspensions in a Newtonian fluid, right? The equations are exactly the same, assuming that, right, for the fluid you're not doing things too quickly, right? So you don't have inertial effects, and similarly for the elastic medium. And so for the fluid, I have a colleague at Penn, Paolo Arescia, who works on complex fluids. He has a rheometer, and with his rheometer, he can measure mu tilde for a suspension of particles. We looked at these monodispersed particles of the same size, and you know, he computed these red triangles that fall in this line here, and you know, if you plot the Hashing-Strickman or PCW estimates in this case, they're this dashed line, which, you know, does pretty well here. This is the Eshelby type result. And if you put, but down here, it's a lower bound, but it's not very good at say something like 40% volume fraction. If you put the self-consistent estimate, lambda equals 1, you get something that's just too stiff or too viscous, right? And so if you put in lambda equals 0.72, you get this this black line here that actually agrees quite well with a well-known empirical expression from the literature in suspensions called the Cruer-Doherty formula. It's not perfect, but it's pretty good. Now, why did we choose this value, 0.72? You know, we can try to fit the data, and you know, we can do that pretty well with 0.76, right? That's the blue line, and it agrees very well with the experimental data. But then, you know, if you have to do that for every microstructure, it gets a little bit complicated. So we want to find a way to find this empirical parameter from something about the microstructure, some information about the microstructure. And the 0.72 we obtained by looking at this result here in dashed line, which comes from an exact asymptotic expansion, Batchelor and co-workers, where they tried to go beyond the Eshelby dilute estimate to incorporate terms of order volume fraction squared, right? And so you can get an estimate for this term of order volume fraction squared, right? And you find that it depends on the radial part of the pair correlation function. Okay? So even just for, you know, the correction term to order volume fraction squared, you need to bring in information about the pair correlation function beyond the angular dependence, the radial dependence. This tells you, on average, how close the particles are. It tells you about the interaction between the particles, right? But it's a very difficult calculation, and it assumes that all the particles are the same size, and it's very difficult to generalize. In any case, we have that result. And if we say, oh, we have this formula here, right, which is valid for any volume fraction. Suppose we take an expansion of this to second order in the volume fraction, right, and we match the term to the exact result of Batchelor's. Well, that's what gave us this lambda equals 0.72. And so you see that you get something that agrees to second order in the volume fraction with exact analytical results for monodispersed systems, and it gives results that are quite reasonable for large volume fractions. Okay, so that's one way to try to maybe choose this parameter lambda. Another way is to look at the other extreme, large volume fractions, right? This method predicts that there is, right, a rigidity threshold, a finite volume fraction where the viscosity or the elasticity blows up, right? That corresponds to the situation where the particles come into contact with each other, right? They form these chains, right? And yeah, the particles carry all the load, and the suspension or the composite cannot deform anymore, right? So if for a given microstructure you have an idea what the percolation limit is, you can use it to choose the lambda from this expression, right? And that gives you, it turns out that lambda equals 0.72 gives you 0.56, which is close to the, it's a complicated problem, you know, particles, this situation where things blow up, and experimentally it's difficult to measure this rigidity threshold, also because when the particles start coming into contact, friction effects are also important. And that's something that we're not accounting for here. But basically, we have a way of choosing the lambda either from dilute estimates or from estimates for the rigidity threshold, and they both give results that are consistent, at least in this case. So that gives us some confidence that this lambda parameter maybe is doing something right. Okay, so that's linear, right? Let's now look at the nonlinear situation, viscoplastic. Again, for the viscoplastic materials, it's easier to do this for suspensions. There are special fluids that behave like ideally plastic materials up to have a yield stress, and then they flow with a power law. So you can describe these materials in terms of a power law. This is the Herschel-Bulkley model. See, this is the yield stress and this is a flow stress. You have both in the same expression, but you can try to generate estimates for both the effective yield stress and the effective flow stress. And that can be described in terms of a power law. And if you make use of our old method that gives a bound, you get this simple expression here, right? And we can compare with the experimental results. And this is what we find, right? This is the effective yield stress as a function of the volume fraction of particles. Again, you have, right, the lower bound, you have the self-consistent, and then you have this, we chose this blue line here with the same lambda as the Newtonian suspensions. Why? Well, because we use the same particles. And we assume that the distribution of particles would be the same. This is not necessarily the case, but experimentally, the distribution of particles when you put the material in a rheometer is not exactly isotropic, but it's pretty nearly so. And what you can see is that the results agree very well with the measurements, the blue measurements in Paolo Rescia's lab, and with other experiments by other groups here in Paris, in fact, that they give results for these types of viscoplastic suspensions. So we're pretty happy with those results. Now, something that you can get out of this homogenization method, right, that you cannot get, you could also do this with some sort of empirical, result for the effective yield stress, is you can now look at the field statistics, right? The averages of the stresses, for example, as a function of lambda. Here's lambda equals 0.72, right? So what does it say? It says that the stress in the matrix goes down, the average stress in the matrix goes down, and it goes to 0 actually at the rigidity threshold, right? So as the particles come into contact, the stress is no longer carried by the fluid, by the matrix. It's carried by the particles, right? So that's what this predicts, and it tells you what the stress in the particles should be. So that's something that makes sense and describes the distribution of stresses in the suspension. You can also get information about the standard deviation of the stresses in the two phases. This is the fluid or the matrix, and these are the particles, right? And this gives us another way to interpret these results. You see that the fluctuations increase with the volume fraction. For lambda equal to 0, the lower bound, the fluctuations actually are bounded in the matrix phase, and they're exactly 0 in the inclusions, right? As you increase lambda, there's sort of a phase transition of sorts at lambda equals 0.4, where you go from having finite fluctuations to having infinite fluctuations. The infinite fluctuations would correspond to situations where you have percolation, right? The particles come into contact. So if the particles are coming into contact, the fluid between the particles, the stresses are have to vary a lot to accommodate the flow fields near the particles, and that leads to large fluctuations. On the other hand, in the particles, you also need to have strong fluctuations, because of course you have to satisfy the conditions of equilibrium and compatibility across the boundaries. So you get this additional information which could be useful for mechanical system. It could be okay. I'll finish with these results here. For a plastic system, right? For a solid system, these fluctuations in the stress can give you information about failure, right? So it's information that you could use to try to develop models for failure of the particles or the interfaces, these kinds of things. Okay, so now if we use this fully optimized second order method, remember that's what we started out with, for these power materials, we get something like this. Now, there is an important detail that doesn't, show when you use the variational estimates based on the bounds, and that is that this effective flow stress actually depends on the determinant, right? This is a linear material, incompressible, isotropic. You can only have dependence on the second invariant. But if you go to something that is nonlinear, in principle, you can have dependence on the third invariant, which is the determinant. So this segment tilde should depend on the determinant. And for that reason, we consider two cases: axisymmetric. So this is, right, you pull in this direction and you compress in the transverse plane, or pure shear. You pull in this direction, you compress in this direction, and you hold it fixed in the other direction. These are two different ways of loading the material that for linear isotropic suspension would give you exactly the same result. But in the nonlinear context, they may not. And in fact, we've known for a long time, these are some FFT simulations, early FFT simulations from the group in Marseille. This is axisymmetric, and this is pure shear. In one case, the fields in the suspending fluid, in this case is ideally plastic, are uniform, more or less uniform. There's some, right? These are the strain rates. Near the particles, you have some intensification near the particles, especially when the particles are close to each other. This is what we were talking about before, right? But otherwise, the fields are fairly uniform. When we go to pure shear, the fields localize on these very sharp bands, right? So even though, right, if you do this for a linear material, you get the same macroscopic response. This suggests that the macroscopic response should really be different for nonlinear materials, in particular for ideally plastic. And so I'll show you what our results give, right? This is the effective flow stress -1. So this tells you the strengthening effect of the particles, right? As a function of the strain rate sensitivity. So here is 1, that's the linear case. As you go down, you go towards the ideally plastic limit. And you see that, yeah, the stress, the effective flow stress goes down with the increasing nonlinearity. These are two different volume fractions. But for shear, you get a softer response than for axisymmetric, right? And this is the variational estimate, which is an upper bound, okay, but doesn't depend on the type of loading. So the results that we get are consistent with this difference, right? And you can go beyond and look at interesting things like, the dilute limits. The axisymmetric case where the fields don't localize, you get a standard sort of behavior that is linear in the volume fraction of the particles. When you look at the shear case, where you have these shear bands which are telling you that the particles are interacting because the shear bands have to meander around the particles, so there's interaction even if you have only a few particles, right? This is because of the changing character of the differential equations, right? You get a behavior that is different. It's volume fraction divided by the log of the volume fraction. The standard assumption that you can just do an isolated particle calculation, right? And then just add the result linearly, as Eshelby did for linear elastic composites, fails when you have these shear bands. So that's an important lesson that comes out of this. These are some plots of the effective flow stress as a function of volume fraction. And you have two lines here that correspond to the pure shear and simple shear. Sorry, pure shear is on top, simple shear is below, different values of lambda. For large volume fractions near the percolation, there's no difference between pure shear and axisymmetric shear. This is because if you have enough particles, the bands have to meander around so much, right? That, yeah, the fields become more homogeneous, if you like, right? Because the bands not only have to meander, but they also broaden when you go around particles. Well, these are some numerical results that show the dependence on the load angle. This is an old method, the tangent second order method, which gave pretty good results for axisymmetric, but down here went down to the Royce lower bound, so it was below the predictions of the FFT. But if you look at that volume fraction here, you see that you don't go from here to 0, you go from here to there. So that's, we haven't done the comparisons yet, but it's consistent with the FFT results. So with the second order method, particularly this fully optimized second order method, in some cases where you don't have strong fluctuations, the tangent second order method works pretty well. But if you go to situations like you have shear bands and things like that, then you need this more sophisticated, fully optimized second order method that takes into account the fluctuations. And I'll finish with these two plots here that show the fluctuations, in fact, in the strain rate, right, as a function of the volume fraction. So as the volume fraction goes down, right, this is the axisymmetric situation, you get what you would expect. I mean, you have some slight anisotropy. These are different components of this fluctuation tensor. But they go down linearly in the volume fraction. You go to the shear case, and the distribution of the fields, because these are different eigenvalues of this tensor of fluctuations, are hugely different, like, 10 to the minus 10. So the fluctuations that correspond to going across the shear bands are finite, right? Because you have delta functions, you're integrating over delta functions, it gives you a finite contribution, right? They don't decay, actually. As long as you have particles, you have shear bands. But in the other modes, the fluctuations decay very quickly, because if the bands are straight, right, the rest of the material is flowing like a rigid block, so there's no deformation. So the method cannot tell you what, where these shear bands are relative to the particles, because we don't know where the particles are, but it can give you information, right, on the distribution of these shear bands. And so with that, I'll finish, and I have to wait for another time to tell you about polycrystals. Thank you.